In this lecture, we continue our study of the transformations of functions by looking at expansions and contractions. There are four basic types of transformations of functions. In the first two types, we simply shift the graph by a fixed amount, either vertically or horizontally. In the last two types of transformations, we expand or shrink the graph by a fixed amount, either vertically or horizontally. In the previous presentation, we looked at translations, or shifts. A vertical shift by c occurred when we simply replaced y equals f of x by y equals f of x plus c. We added c on the outside. But a horizontal shift by c occurred when we replaced y equals f of x by y equals f of x minus c. We replaced x on the inside of the function by x minus c. Notice the subtraction of c. In this presentation, we look at expansions and contractions. What if we want to expand or shrink the image of our graph? We can do this in the vertical or y direction simply by multiplying our function by a constant. For example, if we have the graph y equals f of x, then the graph of y equals 3 times f of x will stretch or expand the graph by a factor of 3 in the y direction. If we want to expand a graph vertically, we simply multiply on the outside by that amount. Here we're trying to expand the graph vertically by a factor of 3, so multiply on the outside by 3. On the other hand, if we want to shrink the graph by a factor of 3, let's divide on the outside by 3. So y equals 1/3 f of x will contract or shrink the graph by a factor of 3. Vertical contractions or expansions are easy to do. You multiply on the outside by the appropriate constant. We could multiply on the outside by minus 1. Multiplying f of x by minus 1 will flip the graph over, reflecting it across the x-axis, replacing positive y values by negative ones, and conversely replacing negative y values by positive ones. This is our first example of a reflection. The graph of y equals minus f of x is a reflection of y equals f of x across the x-axis. We can also expand or contract a graph in the horizontal direction along the x-axis. But just as before with horizontal shifts, because the horizontal axis represents the input variable, the action we take may be the reverse of what we might expect. To expand the graph horizontally by a factor of 2, we must divide x by 2 before inserting it into the function. On the next slide, in thick black ink, is the graph of our parabola y equals x squared. In lighter blue ink is the graph of y equals the quantity x over 2 squared. By dividing by 2, we stretch the graph in the horizontal direction by a factor of 2. Here is the graph of y equals x squared in thick black line. If we divide x by 2, we stretch the graph out horizontally, pulling it out in the horizontal direction. Here's the graph of y equals x squared again. If we multiply by 2 on the inside, then instead of stretching the graph horizontally by 2, we shrink it horizontally by 2. Imagine pressing the graph in. The black curve gets pressed in to become the green curve. And if y is the quantity f5x all squared, multiplying by 5 on the inside shrinks the horizontal direction by a factor of 5. So if we're multiplying on the inside by 2 or 5, we shrink along the x-axis. In summary, to shift the function up by c units, replace y equals f of x by y equals f of x plus c. To shift it to the right by c units, replace that x by x minus c so that y equals f of x is replaced by y equals f of x minus c. To expand a function vertically by a factor of c, merely multiply on the outside by c. To expand a function horizontally by a factor of c, replace y equals f of x by y equals f of x divided by c, replacing x on the inside by x divided by c. We can combine these transformations to create a sequence of transformations. For example, we could translate a function in a diagonal direction, say over to the right by 2 and then up by 2. If we did that, we would replace f of x by f of x minus 2 plus 2. Replacing x by x minus 2 on the inside of the function notation, move the graph 2 units to the right. Adding 2 on the outside, move the entire function up 2 units. Here are some examples. Let's look at the picture on the left in red. What transformation is required to map the graph on the left in red to the graph on the right in blue? If you follow the points, you can see that the point 1 minus 3 on the left went up to the point 1, 0 on the right, and in general we have moved the function in red on the left up 3 units. So our answer is shift the red graph up by 3 to get the blue graph. So if the red graph is y equals f of x, then the blue graph is y equals f of x plus 3. That's easy. Shifting up by 3, just add 3. Let's do another one. Here the graph in red on the left, we seem to have moved it up by 4 and over to the right by 2. Yes, shift the red graph to the right by 2 and up by 4. So if the red graph is y equals f of x, then the blue graph, we replace x by x minus 2 to shift to the right by 2, and then on the outside we add 4. So the blue graph is the graph of y equals f of x minus 2 plus 4. Replacing x by x minus 2 shifted us to the right by 2, and then adding 4 on the outside moved us up by 4. Here's another example. Going from the red graph to the blue, we seem to have merely reflected across the x-axis. So if the red graph is y equals f of x, then the blue graph is y equals minus f of x. One more of this type. In this case, the red graph has been stretched by a factor of 2 horizontally to give the blue graph. So we've stretched the field horizontally by 2. So what do we do if we want to stretch horizontally by a factor of 2? We replace x by x over 2. Doubling in the horizontal direction requires dividing x by 2. Let's look at these two graphs. The one on the left is the graph of the absolute value function. What is the graph for the one on the right? On the right, the original graph of the absolute value function has been contracted horizontally by a factor of 2 and then shifted 2 units to the right, and then up 1 unit. What function then is graphed on the right? First, contract the graph horizontally by a factor of 2, replacing x by 2x. If we contract horizontally, we multiply x. Then shift the graph to the right by 2, replacing x by x minus 2, and then add 1 to the result. So the graph on the right is the graph not of the absolute value of x, but of the absolute value of 2 times x minus 2 plus 1 on the outside. So the graph on the right is y equals absolute value of 2 times x minus 2 plus 1. What transformations, in order, must be done to the graph of y equals f of x to create the graph of y equals 2 times f of x minus 5 divided by 3 minus 7? Let's think about the process of inputting an x value. We want to do the following steps in this order. When you plug x in, the first thing we do is we subtract 5 from it. So we must be shifting the graph right by 5. After that, we divide the quantity by 3. Dividing on the inside by 3 is expanding horizontally by a factor of 3, about the line x equals 5 in this case. Multiplying by 2 on the outside means we expand vertically by a factor of 2, and then finally subtracting 7 on the outside means we shift down by 7. These 4 types of transformation can be combined into a single form, changing f of x into the expression a times f of b times x minus c plus d. That means that first we subtract by c, so we translate everything to the right by c units. After that, we multiply by b on the inside. That shrinks the graph in the horizontal direction by a factor of b. Finally, multiplying by a on the outside, and then adding d expands vertically by a and shifts up by d. We will apply these transformations throughout our pre-calculus course.